Hello everybody. I hope you are fine, doing well during this lockdown period. I welcome you to this lecture number 20 on vector integration. We want to discuss today the volume integral. Before we discuss this volume integral, let us have a review of this what you did previously. Well, you did line integral. I want to just to recapitulate or recap you what we did in previous things where we have done the line integral, how we defined line integral, how we took the curve first, then we divided the curve in different line segments, then we choose the point on that and make this summation tend to infinity. When n tends to infinity, summation becomes this becomes a finite limit. Let us review that concept which you previously did on this. In line integral, what we did is, if you review this line integral, this is the review of this. We considered a curve, because we say what is actually a line integral. Any integral which is to be evaluated along a curve is line integral. Well, if we take a curve AB, we divided the curve in different, this we took P0, then P1, P2, so on to this is Pn point. We divide the curve in finite points first, finite number of points. Then we took here, it is also known as sample point, sample interval. We took here pi minus 1 pi. Then we define the, if f of p is a vector point function which is defined at each and every point of the curve AB. Okay, we divide this curve into finite number of points, P0, P1, P2, Pi minus 1, Pi. Since it is a continuous curve, continuously defined on this finite curve, our function is vector point function is continuously defined on this curve. We took this curve, this part of the curve, this is curve pi minus 1 pi. You can take point here, any point you can take between the curve. Let us take the point here qi we took here. That means your point q1 is here, q2 is here, q3 is here, so on to this is your qi. So this means f of qi is well defined. Okay, if you remember. Then we take the position vectors of this r0, position vector of this r1, position vector of this is ri minus 1, position vector of this is ri. I am just recapitulating you what we did. First we make the number of subdivisions of this curve finite, then in the summation we make this finite subdivision, let it be infinity. Then we consider the sum. We consider the sum, that is summation of I running from 1 to n f of qi into delta ri. What is your delta ri? Where delta ri is ri minus 1, position vector of this point minus position vector of this point. We assumed here, this is the finite sum here, we assumed if n tends to infinity and each delta ri tends to 0, that is magnitude of ri tends to 0, makes this sum a finite, the limit of this sum exists. we said the limit of this sum exists when n tends to infinity, means you are making the infinite number of subdivision points. First you took the finite points, then you make the infinite number of, according to this infinite number of divisions. If the summation of this I running from 1 to n f of delta, this qi delta ri, where delta ri is this tends to 0 when n tends to infinity, if this limit exists, if this limit exists and is finite, the finite value of this is defined as line integral. Then finite value of this is defined as what? As line integral, denotes that line integral of f dot dr over the curve C. This is, you see, in case of the line integral, we took a curve, because we say that line integral is what? It is a this integral which is evaluated along the curve. हमने क्या किया? curve को पहले हमने लिए finite number of points, फिर हमने infinite number of, चूंकि हमारी function जो है ये defined है at each and every point of continuously defined on this curve. So if you take any point in between this, we took a point qi, that means qi can be here q1, q2, it is defined at each and every qi. We find the value of the function at qi, the sum of the product of this and the lengths delta ri. I have given you here the wire what are delta ri represent. It is ri minus 1. What is actually r? Position vector of this. Please, you refer to lecture number, perhaps it is lecture number 9. Lecture number 9 of this vector integration playlist. Perhaps it is lecture number 9, what we did there. So when this limit exists, it is a finite, we say this is the line integral of f dot r. Then what you did afterwards, उसके बाद आपने कहा कि what is the physical significance of this line integral? The physical significance is you can find out the work done by this force along any curve. And it is one more physical significance is it represents the, in fluid dynamics, it represents the circulation. If v is the velocity of any fluid, then you have v dot, this v dot dr, it represents their circulation. You did it. Okay, then you have also done, if this line integral vanishes, in case it is, I am just reviewing your concept, if this becomes 0, if this is 0, this line integral, then what is your conclusion? Do you remember? It is gives the circulation. It is the then we say that it is the irrotational vector. This f is irrotational. Remember this, irrotational. If f dot dr vanishes, then our f vector point function, or you may say force is the irrotational. This is about this line integral. Perhaps it is lecture number 9 of this playlist. Actually, I am just recapitulating you that this in case of line integral, we make the first finite number of subdivisions, then let the subdivisions tend to infinity, then product of these gives you what? Line integral. When this summation, this limit exists, it is here finite summation, we find out it is limit when n tends to infinity, you make infinite number of this summation, this divisions, but here mode of division is in this what is known as it is mode of division is not a fixed one. It is independent of the mode of division. You can take any mode of division. Mode of division is independent. So when this limit exists, we say it is a line integral. Then we did many things on it. Now let us go to surface integral. What you did in surface integral. Let us have. It is just reviewing you. Now in surface integral, what you did, if you remember, we took a surface surface S. This is surface S. Two-sided surface. Then we make this subregions of the surface like this, like this. You make the divisions of this surface like this. Here we take a sample. If you remember, this is delta S1, delta S2, delta S3. Say I take delta Sk. Here I take this kth subdivision delta Sk. Finite number of subdivisions of this surface subdivision. This you take Ni unit vector, normal unit vector to this surface. Okay. Now f is, in the previous case, line integral. In this case also, what was f? F is any vector point function. You can also take scalar point function defined on surface S, vector point function. Then you take here any point here, say pi. Then we find out summation of f of pi dot, and you know Ni is a unit vector, delta Sk when k tends to 1 to n. Finite we take here, finite number of subdivisions. Or we write here I will take k here, I is from 1 to k, sorry, I is from 1 to k. This is, you can write here, this is your ayat Sk division. In this case also we say here first you took finite. If limit of this sum exists and of course is finite as k tends to infinity, first you took k subunits, then you are making k tends to infinity and each Sk tends to 0. If this limit, this is defined as, when this is a finite, this is defined as it exists, this finite value is defined as surface integral of f over the surface S. How you denote it? It is integral of S f dot n ds. This you did about surface integral. That is, in case of the line integral, you took a curve, because line integral is a integral which is evaluated along the curve. We take the first the finite number of subdivisions, then we make the finite number of subdivisions to let tend to infinity, then we take the sum of the products of the lengths and the values of the function at any point of the interval, that is summation of f of qi dot this. Here we take, similarly we take any point in this, we take the value of the function at this point, because it is defined, f is defined continuously defined at each point of the surface. So we find the value of f at pi dot, what is this Ni? Ni is the outward normal to the surface, and this is delta Sk if you take the finite number of Sk this intervals. And when this limit exists, it is finite when k tends to infinity. You can write here also Sk, doesn't matter. When this k tends to infinity, when this is finite, then we say what? This is a This represents the integral. Why did it represent as an integral? I have also discussed it in the this previous playlist, that it is the definition of fundamental definition of definite integral, because it is the definite integral. It works over the range. It has the range, lower limit, upper limit. So it is a definite integral. It satisfies the definition of the definite integral. So it also gives some integral. That integral will be called the surface integral. And for this you have lecture number 14 perhaps. We did it in lecture number 14. Now today we have to discuss the volume integral. What is this volume integral? Actually, if we go to the simple layman's definition, we say volume integral is simply an integral which is to be evaluated over a volume. Which volume? It can be a 3D surface which is closed. Suppose you take a matchbox, it is closed 6, it has 6 faces, it is closed, it has the volume. You take cuboid, you take cube, you take even sphere, or you take the cone. When you integrate over the volume, that gives you the volume integral. Now how we define this? That means in case of the line integral, we took the finite number of subdivisions of the this curve, then we make the subdivisions let tend to infinity, and by the summation, if the limit of that summation exists, it gives the line integral. Similarly, in case of this surface integral, we take a surface, we make first the finite number of subdivisions of the surface, and we make finally the subdivisions let tend to infinity, such that the area of each surface, this is the area of each surface tends to 0. Area of each surface tends to 0, makes this delta Si or delta K tend to 0. Area of each surface tends to 0. When this area tends to 0, when this we make the number of subdivisions we make k subdivisions. When the k tends to infinity, makes each area 0, and the limit of this exists, we say it is a surface. And see, in case of volume, what we do in volume, we consider the volume of certain cube or any closed surface. We consider the volume, we make the smaller volumes, then we let the volumes, small volumes, tend to infinity. The limit, if that limit exists, if that is finite, that gives some integral, that will be called the volume integral. So let us have this definition of, now we come to volume integral. We have now volume integral. How we define this volume integral? Well, dear students, I have just given you the comprehensive definition of this volume integral. That is why I have first introduced how we find out the line integral, how we find out the surface integral. I have already told you, in case of line integral, we divide this curve into first finite number of parts, then make this division infinite. Similarly, in case of surface integral, what we do is we divide the surface into finite number of subregions, then we extend the divisions into infinity, and how that makes the surface integral, and this what is called the line integral. On the basis of this, just look here, I have given you the comprehensive definition. This is your any closed surface, surface S, volume is it is V. What I am doing, I am dividing this surface into finite number of subvolumes. It has volume V, it has volume V, it can be the cuboid, it can be the cube. Don't get confused that we divide this volumes into these squares, or we divide it in what is known as cuboids or cubes. No, you can have the subdivision independent, you can take any subdivision. Let us have the definition here. I am considering any closed surface in space enclosing volume V. It is this. Assuming the volume V be bounded by surface S. It is surface S, it is volume, it has the volume, and fxy be a single valued function, it can be the vector point function or it can be the scalar point function, and our function is defined on the full volume. Full volume means it is defined on the volume and on the boundary of this volume. Everywhere it is defined. So we define, let the function be defined throughout a given region of volume V. Now we divide the given region, that is given volume, into n subregions. Subregions, I mean subvolumes of volumes delta V1, delta V2. It is like this. This is here delta V1, delta V2, delta so on so on. And I take here this sample, I said it is a delta Vi. I took here this ith volume, that is, this is I runs from 1 to n. I am first taking the n sub regions, subdivisions, sub volumes, you may say. That is why I am writing here delta Vn. Let P1, P2, Pn, or simply we write P of xi, yi, zi be the points inside or on the boundary of the subregion. That is, in this delta V1 we have the point P1, and it is defined our function, vector point function or scalar point function. It is defined at each and every point on the volume and on the boundary of the volume. So it is defined at this P1. If we take here P2, it is defined here at PT. Similarly, in this volume that I take here a sample, you may say delta Vi, it is here delta Vi, volume delta Vi is this, and here I take this point, it is not visible here, point is Pi. I take here point Pi in this volume. Pi is the point, just as we take here point in this point, we take P1, we take P2, P3, and we take here in ith this we take Pi. Okay, let's look here inside or on the boundary of the subregions of the volume delta Vi, where V takes from value 1 to n. That means we are taking the finite number of sub volumes. Since f of xy is defined at every point of Pi, it is defined at every point on the this volume. So f of xi, yi, zi, or simply phi of xi, yi is well defined in delta Vi. Then we take here, now we consider the sum, just as we did in case of surface integral. In case of this, when Pi is the point in this volume, delta Vi is a volume, very small, this we took here smaller, these are smaller subdivisions, this is delta Vi. F of Pi is the value of our vector point function, or you may say you have the scalar point function. F of Pi is the value of our function at this point which lies inside this. Then into delta Vi, that is product of the value of the vector point function or scalar point function at Pi into its volume delta Vi. We take this sum, finite sum, where f of Pi is f of xi, yi, zi, the value of the function at Pi, where Pi has the coordinates xi, yi, zi. I am just assuming this. By taking the limits when n tends to infinity, we take here when the number of subdivisions become infinite. Taking the limits when n tends to infinity, that is making the subdivision infinite, such that each volume delta Vi, that is delta 1, delta V2, delta V3, delta Vn tends to 0, and above sum tends to a finite limit, that is the limit of this when n tends to infinity. This, the limit of this sum exists when n tends to infinity and is independent of the mode of subdivision. I have mentioned here that it is not that you will make the subdivision this what is called cuboids or cubes. You can make any type of subdivision, mode of subdivision. The limit of this sum, if it exists, is defined as here from this and there is defined volume integral of f over the volume V, denoted by integral of V f pi dv, or this is integral of V f dv. Now question is, you introduce the triple integral. We express the volume in triple integral. I will just throw a light on that also. You see here how we do that. You should also take, before rubbing this, you should take a screenshot of this. By introducing the rectangular coordinate systems, rectangular Cartesian coordinate system, coordinate systems, that is this. You just take now this volume, this smallest volume element, I will say. You take this as, take this your x-axis, this is your y-axis, this is z-axis. You take this volume, you see how we do. It is this volume element. Volume element, we will say it is dV, your smaller volume element dV. You see, this is our volume element. We took this sample volume element here, which is dV. If we find out the volume of this smaller volume, which is dV, it is this, you see, it is parallel to x-axis, this will be your dx, parallel to y, this will be your dy, this is your dz. So when we find out the volume of this in terms of these Cartesian coordinate system, this will be dx, dy, dz. Okay. So this volume I have represented, this means each and every volume I have represented Cartesian coordinate system. Therefore, when by introducing the rectangular Cartesian coordinate system, what happens? This implies the volume integral V f dV, you can write it is triple integral now. Triple integral over V, phi of dV is your dx, dy, dz. dx, dy, dz. Don't get confused. This is your volume element, smaller volume. You take this volume here. You are expressing this in the rectangular coordinate axis. You see, when you make this volume, smaller volume dV, here it is length, breadth into height. When you find out the volume, it is length is parallel to x-axis. This is dy parallel to axis. Smaller we take, smaller here this is dz is this dz is parallel to z-axis. So this is integral V phi dx dy dz when your f is what? Scalar point function. Scalar point function. This is first. And you can write the same volume here. Just look here. You can write in second condition, you can write it integral of V, volume integral V f dV. You can write it now triple integral over the volume V. This is I times f1 dx dy dz, then plus j times triple integral over V f2 dx dy dz, then plus is plus k times triple integral over volume V f3 dx dy dz. What is this? This is, I will write here, I will mention here this, when, this is when f is equal to f1i plus f2j plus f3k is vector point function. Okay. In case of scalar, you will write this this volume integral dv f of dv. If we replace this f by phi, if our f is phi scalar point, we write dx dy dz. I have given you the explanation. We are expressing this sample volume, that is the smallest volume or volume element, we say this here, and we see when we find out it is volume in the rectangular axis, it will be dv is equal to dx dy dz. So this is your in this case getting this converted into triple integral. Now if it is this, if you are a vector, this vector point function is a vector f1i plus f2j f3k, so in that case you will write it I times triple integral f1, that is component of I, dx dy dz, then j triple integral this, then k f3. So this we come to know by this that volume integral can be sometimes a scalar or it can be a vector according as the function is scalar point or vector point. So this is the something about volume integral. What does volume integral? Now we have next the physical significance. We have given you the physical significance of this line integral. What does line integral represent? If we can, with the help of line integral, we can find out the work done by the force, or in the line integral we can use the line integral in fluid dynamics. It represents the circulation. Then go to surface integral. What is surface integral? Surface integral determines the flux of f over the surface. Flux of f over the surface. Then what about this physical significance of this volume integral? What does it represent? And we will meet next in next lecture. I will give you the physical significance of this, and also I will share with you some applications. Thank you very much. I hope you have understood the concept of volume integral. Thank you very much.